our world and beyond. Space, in partnership with the European Space Agency.
Time and motion. Two essential components to understanding how the universe has evolved. But how it was created remains an enigma.
The universe has a story, and by following the lines of that story, well, it's as if the lines move closer together until they converge at one point into a sort of break point, a point zero, which is sometimes called the Big Bang. A bit of a joke name to show how strange this moment was. So today, our vision is focused on this point zero, and we would really like to know what happened.
The European Space Agency has just published the first results of the Planck mission at the Cité des Sciences in Paris. The aim of this mission, which started a year ago, is to explore the origins of the universe. Project leader Jan Tauber presented the data obtained by the satellite, the coldest spacecraft currently operating in the cosmos.
The most sensitive detectors on Planck, indeed, they need to be cooled to fantastically low temperatures. They need to be cooled to a temperature of only 1/10 of a degree above absolute zero. In centigrade, it's approximately 273 degrees below 0 degrees centigrade. We need these detectors to be very cold, because if they were not this cold, they would be overwhelmed by their own heat, and they would not be able to detect the very cold objects that we're trying to detect.
Launched in May 2009, the Planck satellite is located in a stable zone of the solar system, some 1.8 million kilometers from the Earth. It rotates so that its instruments can establish a complete map of the radiations emitted by the universe in various wavelengths. These fossil radiations resulting from the Big Bang are also called the cosmic microwave background.
The cosmic microwave background is the first light that was emitted by our universe. It was emitted about 380,000 years after the Big Bang, more or less.
The study of these fossil electromagnetic waves, which are now very cold, is essential to understanding the formation of matter and its origins in the universe.
When we look at the early universe with the CMB, with the cosmic microwave background, we see that it is almost featureless. It has no structure whatsoever. So we know that between then and now, there has been an evolution. And we have simulated that evolution, which happens mainly through the work of dark matter. Dark matter is basically smooth when it starts out in the early universe, and it starts by gravity to clump into filaments and in a kind of spider-like network of structures. And the densest points of these structures is where the galaxies will form. Galaxies made of normal matter, the matter that we know and which emits light. So we can only see this small fraction of the universe where galaxies form, stars form, and emit light. But most of the matter is in these huge filaments and structures of dark matter.
Thanks to onboard detectors, scientists have counted some 189 galaxy clusters, 20 of which were unknown until now. These clusters are matter clouds which will eventually come together and form galaxies. Their study makes it possible to understand the evolution of galaxies ever since the beginnings of the universe.
What is most interesting is that these galaxy clusters are like an intermediary stage between the very beginnings of the universe, which you see in the fossil radiations, and a phase much nearer to us.
Une phase beaucoup plus proche de nous, je dirais. Les amas sont, je dirais, à l'interface.
The clusters are like an interface. They represent an intermediate phase, which enables us to better understand, by looking at their formation, traces of the very first cosmic disturbances, back to when the universe was just a baby.
Des traces de ce qu'était l'univers quand il était vraiment bébé.
The charts, which the scientists can now draw up thanks to the time-travelling Planck mission, are full of information. Too much data, in fact, for the specific study of the cosmic microwave background fossil radiations, which is, let's not forget, the primary objective of the mission.
The interesting thing about Planck is it carries two instruments on board. And these two instruments allow it to span a very wide range of frequencies. That means, if you like, colors. So it is observing a wide color spectrum. This color spectrum goes from the long, what we call radio waves, to very short, what we call far infrared. We need this very wide frequency range because the microwave background is radiating only in the middle, but there are a lot of other objects radiating there too. And so we use the two extremes of colors to try to remove all of the radiation that comes from unwanted sources. Parasitic radiation, if you like. Is radiation coming from our own galaxy, but also radiation coming from other galaxies and from clusters of galaxies.
The first detectable radiations, which form the cosmic microwave background, date back to around 380,000 years after the Big Bang. This raises the inevitable question, what was there before? In the Swiss city of Zurich, at the former Federal Observatory, where the young Albert Einstein took his first lessons in astronomy, Professor Benz tries to give us an answer.
Before the microwave background, the universe was very homogeneous, no structures, but it was opaque, like a wall. Now, if you want to know what is beyond that wall, well, you have to drill a hole and get out some material. We don't really know what the universe looked like, but we can probe it, we can investigate it with indirect means.
And at the very start, there was the Big Bang, some 13.7 billion years ago.
So the Big Bang is really the start of time, or the start of the laws. We don't even know that. So we cannot make observations. That is the problem. When we were much closer than seconds after the Big Bang, to fractions of seconds, to a fraction of a billionth or even less, eventually we get to a Planck wall where the current physics completely breaks down. We really don't know what's going on before that.
Will this wall always remain insurmountable? A wall which leaves questions unanswered and which raises even more questions.
We need to keep searching. What could there have been behind it? That's how we'll come up with new theories and technological progress, and how we will push back this wall. A wall which is within fractions of a second of the theoretical breakpoint. But in that fraction of a second lies an enormous number of things. I have to say that some people put a lot of things into it. They put in their hopes, their beliefs, their ideologies. It's their right, of course, but I'd say they must be careful, because this wall will be pushed back one day. It will move. Science will always find out more. Not everything, but we will always know more.
Planck's detectors, which work on a vast range of electromagnetic radiations, could also shed light on another matter which divides scientists: the expansion of the universe, which would have started immediately after the Big Bang. The scientific team behind the Planck mission hopes to bring new insight into this field.
Inflation could have happened in many different ways. And this is what we're trying to constrain. First of all, can we provide, if not proof, at least very good evidence that inflation really happened? So far, we've only known it as a mathematical idea. If we can show that it happened, can we somehow constrain how exactly it happened? What kind of inflation took place? These are the questions that we would like to answer.
Data readings from the satellite are allowing scientific discovery to take giant leaps. However, the more research closes in on the origins of the universe, the more theologists prefer to tread carefully.
One must be careful with the missions we entrust to science, and just as careful with what science doesn't tell us. I believe in separating things. Of course, we must listen to scientists with huge amounts of trust. We need to trust them to tell us how the world works. But when we want to know the meaning of the world, of the universe, the meaning of this big perspective, you need more. You need what you might call the heart or the spirit of mankind, imagination, trust and hope. That's when I believe you have to be very careful not to take your desires for reality, and especially not to impose your desires and convictions on others.
It's thanks to both science and human genius that we can marvel at the Planck time machine, which gives us a chance today to witness the splendid spectacle of our immense cosmic theatre.